Good morning, everyone, and welcome back to everyone who is joining us again from last week, and welcome to everyone who is joining us for the first time. We are Team Lunar ROADSTER. We have Ankit, myself, Deepam. We have Bashwant and Simpson at the operations terminal, and William handling all the logistics for today. And we are advised by Professor Red Whittaker. So, as we all know that humans are returning to the moon, we have the upcoming Artemis missions planned for the polar regions, specifically the South Pole, and the yellow region that is demarcated here uh, represents regions of high interest. So, the question is it possible for a solar-powered rover to repeatedly drive around the moon and never encounter a sunset? Turns out it is, and that's called sun synchronous circumnavigation. Why we need this is that if we have given the smaller size of the moon and the having no atmosphere up there, the high intensity of the solar energy that we can tap into and use for such a perpetual machine will help us explore the polar regions better and create a polar highway of some sorts. We did the math and found that we only need to go at jogging speeds at higher latitudes of 80 or 75 degrees. We need to go at like 3 to 4 kilometers per hour, but that's only possible if the route is flat, circular, and traversable, which right now it's not, and that's where our project comes in, the Lunar ROADSTER. It's an autonomous moonwalking rover that is capable of finding exploration routes and creating traversable surface trails. The primary use case is as follows. We get a map from a previous orbiter mission. We choose a reference latitude, which is shown here in the white dotted line. This would be the current original traversable path, which is somewhat windy around the craters, as you can see. That's where our project comes in, the Lunar ROADSTER. It can select the crater it needs to groom along the pathway. It can also select the crater it needs to avoid while carrying out the task, and it'll start performing terrain manipulation along the path that we have chosen, ultimately creating a path which is more circular and hugging to the reference latitude that we earlier chose. While we prep with the demonstration, I'll go over some of the highlights of the rover. So it sports a 60 centimeter dozer blade with very high tool actuation strength that makes it 3 times stronger and bigger than the predecessor. The custom wheels with high rim pull and maximized grip paired with the high torque drive actuators gives us superior pushing power. The reliable circuitry and the custom designed power distribution makes it an optimal specialized machine for crater grooming. Let's look at the demonstration.
So moving on to the demonstration, to talk about what's different today from last week. Last week, we used the total station for localization. What's different is that we're imagining a scenario where we don't have the total station, which would look like something like this, where a asteroid or a meteor hits our total station. So now we have to use something that is a fisheye camera. So since we're not using the total station, we'll be removing the prism that is on the rover, and we'll be localizing just based on that gimbal and fisheye camera that is currently on the rover. So for the demonstration, the mission statement remains the same. That is, the roadster must use the excavator to groom multiple craters around the path, around the moonyard, and create a circuitous traversable path. So for the procedure, in our pre-demo setup, we prepare the test environment that is creating all of the craters. We obtained the global map using our laser scanner. This laser scanner is used to emulate the lunar reconnaissance orbiter data, or 2D map data that we would get while on an actual lunar mission. We set up the operations terminal that Bashwant and Simpson are going to be monitoring the mission from. We calibrated our localization. We set up the new GUI that you see here, which is still being loaded, and we send the start mission command. So during the demo, when we send the start mission command, the roadster is going to traverse to the first crater. It's going to perceive the crater and figure out crater geometries such as centroid, diameter, etc. And it'll plan a manipulation plan to fill the crater in and create a traversable path. After it does the manipulation, it's going to move back and validate the system. The validation criteria is based on gradients that we'll explain later. And once the manipulation is validated, the roadster will move on to the next crater until the mission ends. So while we do get set up, our roadster has been experiencing what we're calling at this point Encore jitters, because since morning we haven't been able to get our network set up, like our local network that we used to launch the Jetson. Essentially, open the terminals on the Jetson has decided to not work for us, which it has never done in the past 1.5 years. So we'll still be struggling with that, I think. If it does work, you'll see the roadster move. But other improvements that we made from last time was the GUI. So, okay, it looks like the mission is going to start soon. But on there, I'll talk about what's different. So the first thing that we did is for Encore, you guys suggested that the tool height should be adaptive. In the sense, so what we did is we're starting to use the point cloud on the Z to figure out the max elevation and crop the crater region to find an optimal tool height. So it looks like it's moving. So I'd request all of you to come over here and watch watch as it does the manipulation. So currently the rover is in the perception state. In the perception state, we in the perception state, the Roadster is supposed to use RGBD frames from Z camera to detect the crater. We've trained a custom YOLO V8 model that gets the geometry extraction. That is, we get the centroid of the crater in the world frame as well as the diameter. Using this, we plan a manipulation that is done in 4 poses. These 4 poses are source pose, sink pose, source backplate pose, and sink backplate pose. So our manipulation is divided into a forward pass that is frontal grading and a backward pass that is backward grading. So when it does start moving, you will see the source pose where the tool will go down. Then it'll go to the sink pose, which will be about half of the crater. Then it'll lift the tool back up, go to the other end of the crater, which is our source backplate pose. The tool will go down again and finish off with a clean backblading pass. So yeah, the errors that you will see today are attributed to the new localization system that we're using. That is the seal track. And while we did test the tool heights tool planner subsystem, what we found out that the heights that it gave out were pretty similar for each crater. So it will look pretty similar to what it looked like in the last demo, but we do have an adaptive methodology. So to talk about the new localization system, the fisheye camera that you see mounted on the gimbal is looking at the lights on the ceiling. So we're getting the fisheye image of all of the lights on the ceiling. And then based on that, we're masking out to find the bright pixels to localize the lights. In this image that you see on the GUI here, there is a preset grid that is going to regress to each of the points. That preset grid, when it regresses to the points, we find the residuals. And using that, we're able to find the pose of the rover in the moonyard. In the 2D moonyard, and further we reprojected back to 3D to get our 60F pose, using it with our Kalman filter for the wheel encoder as well as the IMU. So in this, the first pass has been completed. If the localization is correct and it's clearly looking at the crater, this should output a validation false. That means the crater is not groomed enough, and hence it should do it again, and which is what we hope will happen now. It passed. Okay. So yeah, why the reason it passed is because the Roadster moved back too much, in the sense that we look at a very centralized region in front of the blade to where the crater is supposed to be. So it moved back too much, and that's why the validation passed. So now it's going to move on to the next crater, looking at and execute the same process again. So while it does do that, I'm going to talk about the navigation subsystem. So the circuitous path that the Roadster will follow is governed by a global nav planner, which is a lattice A-star planner with Ackermann primitives. What that means is, since our Roadster only can do Ackermann steering and can't move leftwards directly or rightwards directly, we need to generate paths which are actually executable by the Roadster. So this is done with Ackermann primitives. It heavily penalizes sideward motions as well as backward motions during the global nav state. Once the nav planner gives out waypoints, it is then sent to our global nav controller, which is a pure pursuit controller, which executes the motion. In the manipulation state, we use the same global nav planner and the global controller with slight differences. The differences are that in the controller, we will now allow backward motion so that the backward pass can be completed. This is done by giving look ahead distances towards the back so that the backward motion is executed. So on the GUI here, the blue ring is the reference latitude that we're using. The yellow ring is our reference ring. The reference ring is what there are 2 things about this. It must reach all 4 gradable craters as well as fit as close as possible to the reference latitude. That is what makes it circuitous. So on the map, you would see there are 5 craters, but at the beginning of this, there were only 4 craters in the moonyard. This is because this crater on the leftmost, leftmost crater is something we're trying to demonstrate as a phantom crater. That is, we have data from the LRO that would say that there is a crater here, but the roadster will go there and it should hopefully realize that there is no crater there and just move on to the next one. So now that the manipulation is executing, yeah. So while it completes, I can explain the overall flow of our system. So when we send the start mission command, it is sent to our global nav planner. The global nav planner uses the 2D cost map to create the reference ring, and the reference ring is used for our global waypoints. The global nav controller will then use these waypoints to execute these motions. Once we reach the crater, the first thing we do is run the validation subsystem. Since the manipulation has not happened yet, the validation will always output false. When it outputs false, the perception subsystem starts. And currently in Encore, we also have a tool planner state, which is using the RGBD point cloud data, using the Z point cloud data to get the optimal tool height. Then the perception subsystem gets crater geometry and plans robot poses. Then it sends it to the manipulation planner. The manipulation planner is a modified global nav planner that will help execute the plan paths. Once all of the plan paths are executed, we go back to the validation state. If validation will output failure, we should manipulate again. If validation outputs success, we should move on to the next crater, going back to the global nav planner and the controller until the next crater is exceeded. Once all craters are finished, we should send an end mission command and a stop, and the rover should move to the stop state. There is also a demonstration video playing on the slide if you want to look at it while the mission is on. We'll explain some results that we got after the mission is finished. In the meantime, if you have any questions, we'd be happy to answer them.
In this case of the second crater, do you think it was looking in the right place and the validation is correct?
Guys, was it looking in the right place? It wasn't? No, it wasn't.
Are you experiencing the issues that you mentioned at the beginning of the network?
Yeah, essentially what is happening is a lot of our communication happens over our Lunar ROADSTER network, whether that is even starting off the terminal inside the Jetson is done over the network. So all of that is being delayed for some reason. Nothing seems to be working at the pace that it's supposed to be working at. So we don't actually know what state inside the Jetson is running currently because the network delay is just that bad.
The people at the operations terminal also, they've been monitoring consistently, but as he mentioned, like when it's in validation state, actually we probably see a different state there. So
yeah,
it's hardly deterministic at this point. So right now you must have seen that it went to the third crater where it was supposed to see a crater based on the map it was given, but there was no crater. So it gave a validation success and we found that there's no crater and we're moving to the last one.
What is the frequency for the SkyCam? Like odometry frequency?
Do we know the frequency right now of the SkyCam?
I mean, in general, even if like, let's say what is the
30? That's 30 hertz.
It was supposed, yeah, it's ideally supposed to be 30 hertz.
Ideally.
It's supposed to be 30 hertz. But again, what you see here is over the network. What you see here is over the network. What is happening inside the Jetson could be 30 hertz, might be 30 hertz, but here it's all happening over the network, which has decided to not work today. So
we also included the continuous YOLO visualization, as you mentioned, but we're just not able to get it through the network for some reason.
Yeah. Oh, and we were able to get rid of the circular parts that were happening. Now you would only see like a feasible one red path on the GUI. That is what the rover is executing.
an orange and a yellow, but I assume
The orange is the reference ring that we talked about in the beginning. That's the.
So
is
this
orange and a yellow, or
this orange is the
There's a
current path that the rover is following.
I meant the orange and the yellow.
This
I
one?
don't know if
No,
that's
it's
a
only
boundary.
one.
Oh,
It
that,
is,
that
yeah.
might be one.
Yeah, it's just one. Any other questions?
Is there any implementation of the automated wave type setting?
Yeah, there is. Currently, that's what the automated tool planner state is what we discussed. That it looks at the crater to find the optimal tool height using point cloud data. But what we've observed is that the point cloud, whatever it outputs, is very similar to what we were setting manually anyway. So it will look very similar to last week's demonstration, but the automated tool thing is working.
It gives the impression that the blade is never dropping far enough. So,
I think if we are able to see a second pass, which is only seen when the validation fails for the after the first run, that's when it tries to go further down to make sure that it grades it better. So for the first two craters, we couldn't see the second pass because validation apparently gave us success. But right now, if it looks where it's supposed to look and we get a validation fail, we'll see a second pass and hopefully the tool will go down further.
So in the second pass, we manually offset it to be a lower tool height for sure, so that we're able to get a better finish. But yeah, we haven't been able to see that because validation seems to be passing for each crater.
For some reason, maybe it's impressive. It seems like it gets missed.
Yeah, that's the localization error. Yeah.
I think that
Okay.
Okay, the second pass is happening. We'll see it happen. So yeah, the localization error is based on the new localization system that we're using. That needs way more tuning. It does work much better than we expected it to in the beginning when we came up with the idea. But yeah, it requires some more tuning, and even the fact that we're leaning into this, we get into the fisheye camera view, and that disturbs it. So we realized this today also because we were testing with this thing down the whole time. And now that we started leaning into this, in the beginning, the fisheye camera, we come into the fisheye camera view, and that caused problems. So yeah, it's a work in progress, but we're quite happy with how it's working currently. It's much more better. It's much more lunar accurate, and we're also happy with the fact that it can do at least this much.
and there's no latency as it was.
Yeah, there is way less latency because even during with the survey gun, what used to happen was that would get the data, then we would send it to a laptop or a TX2, then publish it onto the network. The Jetson would access that network, so that there was a big latency there. Now that the seal track is working on the Jetson directly, we'll get a much better frequency of updates from the seal track system directly.
I have no idea what it is.
We will. Yeah.
Is that thing localizing within 10 centimeters or 20 centimeters or 5 centimeters?
It from what we've noticed, when it is working well, it is giving us better localization than the total station itself because it's much more continuous.
How are you getting the ground truth?
It's ground. It's not a model. It's
No, as in like, how would you know what is the accuracy of the odometry? Because I assume your ground station is your ground.
it is the ground truth. Yeah.
Right. So how would it be?
Because it updates better. Like it updates at the frequency better.
Frequency is better.
Yeah.
But what about the accuracy?
So
if you run them together, like if you have a total station frame as well as the seal track frame together on a map, they're almost overlapping.
Okay.
Yeah.
And to ensure that we have the while initialization, that's why we have the prism on first. While initialization, we do need some ground truth correction from the total station, and once we get that, we don't need the prism anymore.
But you don't need to throughout the process, like
No,
No.
right now, no. So you can see total station is not even looking at the rover right now; it's looking somewhere else.
That's why we took the prism off to show that we're not using the total station at all.
Yeah.
Go.
Alignment to the cost.
All right. So right as we completed the first pass and we are doing the circumnav demonstration, I'll go through some of the results that we collected through bunch of tests over the weeks. So starting off, the Roadster plans a path with a cumulative deviation of up to 25% from the chosen latitude's length. So as we see in the visualization here, the blue ring is the chosen latitude, and the yellow path that we plan is the reference ring that we create based on the map that we get. This error that we get from how far it is from the reference latitude is the deviation that we're talking about here, and it arises from the untraversable terrain like the craters that it. Oh, okay. Yeah. So the reference latitude is not exactly hugging the reference ring is not exactly hugging the reference latitude because of untraversable terrain like the big craters or any other obstacles in between, and it also makes sure that it fits to the gradable craters that we chose. So that's where the deviation arises from. Through a bunch of tests, we found that the least deviation we get is 21.47%. Max was very close to our limit, 24.3%, and the mean was 22.89%, which satisfies the requirement. Similarly, the roadster follows the planned path to a maximum deviation of 10%. This deviation occurs due to the localization or navigation errors that we just saw. So it tries to follow the yellow path that was created, but due to some localization error or navigation error, it tries to swerve around, and that adds on to the deviation. So in our best run, we got a deviation of just 0.09%. The max deviation we got was 12.98, but the mean was well below our limit, which was 7%. Next up, we also calculated the contact pressure of the rover. We weighed the rover, and based on the contact area of the wheels, we found that for a gravitational location like Moon, the contact pressure is 1.37 kilopascals or 0.19 psi. That's well below our limit of 1.5 kilopascals. We did the same analysis on different locations like Earth, Moon, and Mars, and we did that study to see how much contact pressure we would get and relate that to the sinkage of the wheels and the rover itself. Next up, as we saw that once we get the map, we carry out an analysis to see which craters it needs to groom and which craters it needs to avoid. That's the capability of this rover, that it can select the crater it needs to avoid, which is the big crater that we see on the far end there. Since its size was greater than 0.5 meters, it intelligently selects that as an ungradable crater, and it only gives the coordinates of these 4 craters to the global controller. Yeah, and along with that 0.5 meters, we demonstrated that the rover has the capability to groom the craters which are up to 0.5 meters, so it can be 0.2, 0.3 in diameter, and up to the depth of 0.1 meters. Let's look at some requirements we satisfied.
So moving on to functional requirements, we were able to demonstrate most of our functional requirements today. That is trail path planning, operating autonomously, localizing itself in a GPS-denied environment. That we've done in 2 different methods now. That is total station as well as the sealed track. We've navigated the planned paths. We've traversed uneven terrain. We've chosen the craters we want to groom and avoid. That is done that is shown in the GUI there. We have graded craters. We've validated the this grading, although not very well today. And we're communicating with the user, that is the operations terminal, as well as the GUI here. For our non-functional requirements, these remain the same as last time. We achieved our weight, we achieved our cost. We're able to run everything on the onboard Orin. We have technological extensibility. That is, we have a very extensive wiki that we're planning to give to our successor project if there is any. The rover must look good. Red agreed that it does, so that is also verified. Modularity, we can take off the current tool of the Roadster by unscrewing 3 bolts and also just mount it back just as easily. So that is also achieved. And repeatability, we have completed multiple missions without the need of maintenance, although today was not one. So that is the end of our FPD Encore. Before we move on to Q&A, we would like to acknowledge some people without whom this project would not have been possible. Professor Ed for being our project advisor, Dimi and John for being our course advisors, Tim for being our workshop supervisor and helping us with all building, Team Crater Grader, who is the predecessor to this project, and we built off of their platform, Dr. Venny for helping us with the laser scanners, Chuck for helping us with the total station, and Dr. David Wettergreen for letting us use the PRL. So thank you, everyone. We are Team Lunar ROADSTER, and that is our FPD Encore demonstration. We have time for questions.
We have a couple minutes.
Yeah.
I don't know if you tried more different crater geometries to groom, maybe a little bit more aggressive in scale so you can solve the grooming. I understand that.
Okay.
But that may be worth once this is all over, basically, to try different forms of craters, different geometries of craters, and see how it works, just to get some more results.
So yeah, throughout the testing process, we have tried multiple things. If we go above the tool blade or like the 0.5, what basically happens is the side berm is not going to be affected, like it's just going to be there, and what the wheels just drive over it, so it becomes like a valley. If you go bigger, so if you want to groom bigger craters, either you can increase the tool width or you can attack it from multiple directions, which is what Crater Grader did when they were trying to do a bigger crater. So yeah, that is what we've seen.